Hello, folks. How are you doing? Glad to hear it. Make sure we're all good here. People making good progress on the homework? Good, good. I have just given the order to our intrepid TAs to also post what solutions look like to help you guide you on your process. Because again, it's the journey. Yes, checking the answer at the end is great, but it's a good way to check your process along the way. Okay, so hopefully we're moving forward on that. Again, this is sort of a rite of passage for a lot of folks. You're coding up your own neural networks, with multiple neurons per layer here, in order to actually, like, from scratch implement this stuff. That way, when you're using Keras or using TensorFlow or using PyTorch or whatever you're doing in your career with machine learning, you know what's happening under the hood. That's really important as far as my concerns for the process here. So feel like so. Also, sorry I didn't have a lecture last 2 Thursdays ago, as I had so many backups for my travel setup, but they all basically exploded. So anyway, I'll find some other way to make it up for you with some optional material to catch up at some point. Okay, so for fun, not required. So we've done a lot with different types of structures of neural networks. We talked last in-person lecture. We were talking about all different types of optimization algorithms. That was what I was hoping to cover on Thursday, was more advanced gradient descent types algorithms. So we'll instead do that this Thursday. We'll cover that. So things like Atom, okay, or momentum-based optimization algorithms, right? But we've also covered kind of a couple of different, let's see here, couple of different approaches to machine learning, the paradigms of machine learning. I want to make sure you get at least a flavor of each of them. Okay, so let's go back to here. Let's see, 2026, 03, 24. Okay. All right. We've covered different paradigms of machine learning. We covered supervised learning a bit, more than a bit, the most. We did a little bit of unsupervised learning with a little bit of clustering, just a little bit, just a taste. Okay, anyone remember a third important paradigm of machine learning? Anybody? Reinforcement learning, my personal favorite. Okay, that's what we're going to be covering today, an introduction to reinforcement learning. Okay. Lovingly abbreviated RL. Okay. Now, I love reinforcement learning for a number of reasons, mostly because it's more related to my own personal research that I do in my laboratory. It's more related to control and robotics, not just robotic control, but all kinds of control. But really, anytime you have to make a decision in an environment, that's something that is typically shaped by reinforcement learning. It's not the only thing. Okay, so reinforcement learning. Now, the wonderful starting point for anything reinforcement learning, that's not even like, it's one of our textbooks. It's free online textbooks that they have for this, but it's Sutton and Bartow. Okay, all right, they have the entire textbook is it's filled with information. What you really want to start with is the idea of what's called dynamic programming. You want to read more. Okay, I'm going to give you a broad overview of what reinforcement learning is about and how we could get started with this in future coding lectures. Okay, I love the Sutton, it's Sutton, not Sutor, and Bartow textbook. When I was a master's student, I had a project. I was very lucky. I had a funded project that was on walking robots. Shocker. Okay, but I was really lucky. I had license to kind of do whatever I wanted, which is a scary thing for a grad student. Okay, it's a vast open world of different ways to control walking robots. And I was reading a cool paper that just incidentally talked about using reinforcement learning, and it pointed me to the Sutton and Bartow textbook. And I remember I printed off the PDF of this textbook, okay, and just legally printed off the PDF of this textbook and just read it over spring break. And it just really changed how I viewed algorithms for robot control. It's just really interesting. It wasn't super useful for me. Like I used it in my master's thesis, but like it was kind of hard to get working. But things have gotten much better in the last 5 to 10 years in reinforcement learning, specifically for robotics, but in general. Okay, the advent of deep learning is really turbocharged how reinforcement learning works. But the Sutton and Bartow book, it's called Reinforcement Learning, but these chapters, really starting with chapter 4 on dynamic programming, is when it really starts to get juicy, in my opinion. So you can check that out. So I'm going to be going over the basics. So one thing that is important in reinforcement learning is the idea is that in reinforcement learning, trains a policy which reads a current system state and outputs an action in a way which maximizes a reward, okay? Specifically, the reward is evaluated by interacting with an environment. Okay? Now, this reward, this thing that you want to maximize, it sounds a lot like minimizing a cost function or minimizing a loss function. It's very similar. Okay? Who gets to choose what that reward function is? We do. We do. That's an important choice in reinforcement learning. And we'll get to why in a minute, okay? But there's a couple of key terms here, all right, that we're talking about. One is, so we have the idea of a system state, okay? A state. We have an action. You have a reward. Okay. And in the middle somewhere is something called the policy. Okay. A policy is something which you take in a current state. Whatever that state is, then you output an action. Okay. Obviously, this you can see how this is near and dear to the heart of people in robotics, right? We say our system state, that's what we are. That's where we are. And the action is, what do you got to do? And this policy is just mapping one to the other, a mapping from state to action, okay? If you're in a control systems class, you could easily just call a policy a controller. Sometimes we call it a control policy, okay? That they're very similar. If you are taking, I don't know, a course in, say, applied optimal control, just as a random example, all right? There's a lot of parallels. We talk about system state. We talk about action, which are control efforts, and then some controller in the middle that determines what to do. Extremely similar. It's just that the history of reinforcement learning was very much in the sort of computer science, machine learning world, and the history of control comes from a much more, a different kind of mathematical discipline of control. But they're talking about different things, okay? So a policy, the policy maps state to action. Okay? Here's an example. Someone pinches me. Ow. I sensed pain. My actions say ow. Recoil, attack. Whatever my response is, that's my policy. What I decide, the decision that I make is in here for what action I take. So the learning and reinforcement learning, what are you learning? The policy. Okay. Reinforcement learning is about learning a policy. Okay? So let's say you have your, so the idea is that if you have, so typically the policy, sometimes you'll see this in a textbook, might say letter P, nay. No, we're not saying P. That'd be way too simple. Whoa. We just missed Pi Day. But we actually say pi is a policy. Okay, not the number pi. It's just treat the pi as it's always a letter. Okay, so policy often, and there are many different notations. This is the one from Sutton and Bartow with maybe some revision. Okay, you have some action A, state S. If you were in a controls class, not that I know anything about that, controls, you would say that that's the state is X, right? You would see that as state space, all right? And your action in controls would be U. If you're thinking about this in terms of a typical control systems class, if you take controls 1, this is the state space controls part, okay? So, but this here is how it's notated by machine learning researchers, machine learning practitioners, okay? So you would say that, oh, A is going to be equal to pi, which is some function of state. So gives you an action. Okay. Okay. But what policy is a good policy? Well, the one that maximizes our reward. Again, a thing that we define, okay? So we create something called a reward function. Let's call it R of S and A, okay? It's a function of maybe where you are and the action you take, okay? Where positive is good. So bigger is better. Higher is better, but bigger is better. Better way of thinking of that. Unlike a cost or a loss function, lower is better, right? So if you're going to do reinforcement learning, you have to devise a reward function, okay, that is going to encourage the behavior you want out of your policy, okay? So to demonstrate this idea, let's see here. Okay. Hopefully people can see on the ground right here, there's sort of tiles on the ground, sort of these squares. You know what squares are. It's not that soon after spring break. We remember our shapes, okay? So to speak. We're doing well? Perfect. We looking good? Oh, well, wonderful. What a great way to start spring break. Okay, so a classic example of a reinforcement learning problem is coming up with a policy to navigate a grid of squares, where your world is a grid. They call it grid world. People are very creative. Okay? Well, the idea is you have some kind of target. Let's see, let's grab some useless piece of equipment like this remote control I never use. Okay? Here's my goal. Okay? I want to get there. I have all these squares. I start here. Okay? I can move up, down, left, or right, like an old school video game. Okay? And I want to find out a way to get to the goal square where the remote control is. Okay? The square that I'm standing on is my state. This state, where I'm standing, represents everything I need to know about my current, about where I am in the game of getting to the end, right? I don't need any other information than that. Okay, I'm here. If I booted up the game right now, the game right now, and I saw that I was here, oh great, that's all the information I need to know. Okay, so now me as a intelligent person knows a policy that would get to the end. It's like, hey, I'm going to go in that direction until it's to my left, and then I'm going to go left until I'm there. Okay? So policy, boom, 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 boom. I'm changing my state with every square that I step into. Each state is each square is a new state that I'm in. My action was go toward the front of the class, front, 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 right, 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 and I'm at the goal. Okay? That's what I want to happen. But in order to do reinforcement learning, I have to reward behaviors that are going to get me close to my goal. Okay? One very simple reward is, will this action get me to the goal? That one doesn't. That one doesn't. They're all bad. Who cares? However, my friends, I'm standing over here. There is one action that is a very good reward. I could say that gives me 1,000 points, right? That gives me 0. That gives me 0. That gives me 0, right? Which action should I take? The 1,000-point reward. Holy Hannah, well, look at that. All right, I designed my reward function. It works really close to that goal, right? That's good. However, it's no good over here. I'm 2 steps away. Reward 0, reward 0, reward 0, reward 0. Okay? So people found out a long time ago, it's not enough just to say, hey, this is my ultimate reward. It's to get there at the end. Okay, because it won't know what to do if it's many, many states away or a long while away, right? Now, I'm sure in your own heads, you're like, who in their head right now is engineering a new reward? Anybody? Am I thinking one? Yes, I see. Angela, what reward are you thinking of? Correct. So you're talking about, hey, what if you had a reward that is decreasing distance, right? Not a bad one. Not a bad one. That actually would work really well. Basically, imagine it's sort of like the inverse of the distance away or something that rewards smaller distance. Okay, that could be your reward. You have shaped your reward where if I take a step in the direction of maximizing reward, it should be able to get there. Oh, that's great. Cool. And in this simple task, you will have succeeded. That's great. Now, what if instead, though, what if I start putting up walls? Let me see, where's my wall, 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 wall. Start here. Your idea is great. I'm just going to shoot it down, if that's okay. All right, Angela? All right. Now I have Angela's reward. Try to get closer. All right, get closer. Boom. Get closer. Boom. Stuck. Anyone I want to go, I have to go around, increase my distance, right? No bueno, not good. Okay? So, yes, you could be really clever with just the immediate reward that gets you closer to your goal. Or you could be a little bit more thoughtful and more general. Instead of thinking about immediate reward for being close, yes, we know for a fact if we end at the goal, that's really close. Maybe there's the idea that certain states are better to be in. Angela was sort of encoding this intuitively by saying, hey, being closer is better, right? What if we could generalize that, okay, and say, hey, if there's a way of saying, hey, this state, I'm not at the end. It doesn't give me a reward. This is the reward. But being in this state is more valuable than being in this state, right? I mean, why is it more valuable? Because I know I'm close to the end. Okay? And this state, it's pretty valuable. Maybe not as valuable as that. Why? Because, well, what if I instead try to seek out a state that is more and more valuable? And that will take me closer to a higher reward state. Okay? So people have invented this idea of a value function here. So here we go. The idea, so the reward functions can incentivize actions that achieve a clear, desirable result, or the opposite. You could say a huge negative reward. What if you stepped on the obstacle? Negative a million, right? You do the opposite. Or the opposite. Value functions can incentivize moving to states that are more likely to achieve higher reward in the future. Where you have some V of S. It's dependent upon the state that I'm in. Intuitively, in ways I haven't defined yet, I kind of get the fact that over here is less valuable than being right here. But being right here is better than being on the other side of the wall, etc., right? So is there a way to learn the value function? Okay, so for now I'm gonna actually start to draw out this grid world example. So the value function. Okay. Value function depending upon state, right? Let me sort of motivate a way we might be able to build this value function. Yes. Ooh, is the value function the same as heuristic? It's not the same, but it is similar in concept, right? It's like, so you're referring to a heuristic in like an A-star search algorithm, right? A heuristic and A-star search algorithm, like, so probably one of the best ways to solve this exact problem of the grid world, of the grid world, is to do what's called like an A-star grid search. And those require something called a heuristic, which says, here's a very simple thing I can compute that I could not, a number that says I could not possibly outperform. So one would be like the distance to the goal. There's no way I can get a closer shot to that goal than the actual, like, as the crow fly distance. It's impossible, right? And that's what a heuristic is in that. A value function is just a way of assembling a meaningful mapping of how useful a state is. Okay, it's a lot more general. A heuristic actually has very strict requirements for what it must be. Okay, good question. They're very similar in concept. All right. So higher reward in the future, right? So imagine. Let's just sort of motivate this. Motivate with a grid world example. Okay, and conveniently, my iPad already has a little grid here. Oh, beautiful, wonderful, awesome, cool, nifty, neat. So we're going to have my grid. Okay, my grid is like 8 by 8. Okay. 1, 2, 3, 4, 5, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Those are just grids, okay? Here's my goal, okay? And whichever block I'm in, that's in a discrete state, okay? So we'll call the state that I'm in, we'll call that's an agent. This is where our agent is, in that state. Okay? This is our goal. Okay? And let's establish a reward function where R of S is just a simple when statement. It's 1 at the goal, 0 otherwise. Okay? Exactly what we talked about before, right? Go over that. 0, 0, 0, 0, 1. I'm at the goal. Okay. All right. And what we want is a policy that somehow going to get us to that goal. And in fact, we're going to start just blocking off some of these states. I'm just going to make a little wall right here. Happy little wall over here. Okay. And now I'm going to create something. And technically speaking, a reward can also include the action. For instance, like if you take an action, you could say, oh, that's like a negative reward because, you know, taking action, you want it to penalize taking actions, meaning you want to get there fast, right? Something you could do. This is a very simple reward, right? But let's create, imagine you had a value that you're going to try to just update over time with an increasing sort of iteratively, okay? So we know that the goal here, this gives us a value of like 1. If we're, sorry, a reward of 1. Let's say we had a value function of a certain state, which is equal to the maximum reward across all actions, for all actions A that you could possibly take, okay, at the current state, and the maximum reward. And we'll say Si plus 1, this means to be the next state, taking a step. Okay? The value is going to basically say, hey, whatever state you're in, if you take all the actions you could in that state, whichever the best action is, what's the reward of that? Okay? And then we're going to multiply it by some number, gamma, called the discount factor. Discount factor. And it's between 0 and 1. That's little gamma. Okay? Let's just say it's, for our sake, it's 0.9. Okay? So that's the value. The value is that, hey, the value of a current state is equal to whatever the best reward I can get on my next step. Okay? Times 0.9. Okay? So that means right here, so right now, if I'm trying to compute the value of remote control that you can't see, right now, my value is 0, value is 0.9. I'm close to that goal. That's good. And if I'm at this goal right here, I'm already at the reward of 1. That's great. But the value here is 0.9. Okay? Interesting. Right now, so I can see then how if I have a value, let's put it in value right here. The value here would be 0.9, 0.9, 0.9, 0.9. Okay. Interesting. Imagine I could propagate these numbers out to like 0.8, 0.7, 0.6. And all of a sudden, you can imagine that like, oh, now I have a very clear map of how to get to my goal in a really fast way. You change the math up a bit, right? So maybe instead I'm going to mess with the math here, because right now, if I'm at this goal, this state right here, there is no reward for going this direction, only improved value, right? There's still no reward. You don't hit the end. There's no nugget of gold at the end that's your reward. You just say, hey, there's this nebulous notion of value nearby. So I need to change up my formula. So instead of doing the max reward, I'm going to say, I'm going to get rid of this here. I'm going to say the maximum of R plus the discount factor times the value of that state, right? Okay. The value, what's going to happen is if I now have a value function that's dependent upon the value function. Whenever you have that happen, what's going to happen is you're going to iteratively update it. Just like you're starting with your initial guesses in your gradient descent, you start off with a guess, then you iteratively update the guess until it's good, until it converges. Same thing here with the value function, okay? So you might assume that the value across all of these things is zeros. Then maybe you go across all of the different states and say, okay, after one pass, I would update my value function. That's basically just numbers in these grids, okay? Oh, it's 0.9, 0.9, 0.9, 0 everywhere else. Okay, now let's update again. Now I'll go across 0, 0, 0, 0, 0, 0. But now, when I get to this square right here, it's going to be the maximum. There is no reward because I'm not next to a goal, but the best value I can get is 0.9 times 0.9, which is 0.81, which I will generously round to 0.8 for the sake of my squares, right? 0.8. 0.8, 0.8, 0.8, 0.8, right? Do another pass. What's going to happen? 0.7, 0.7, approximately 0.7, right? And very quickly, it's going to propagate out to 0.6, 0.5, 0.4, 0.3, 0.2. It's not actually literally those numbers because they don't actually go negative, right? It's just multiplied by 0.9 over and over again. But it's very going to clearly point me in a direction of going, right? So we can use the concept of value and iterative updates on the estimate of value to guide a policy toward a distant reward. Okay? So that's how we can take a reward that's just very near-term looking, try to turn it into a long-term policy, even though it can't see the reward right now, right? Okay? I mean, this applies to many sorts of systems, topically enough. I mean, like the game of Survivor, you want to get to the very, very end of the game, but you also don't want to get voted off right now, right? I mean, so theoretically, the reward function is get to the end, win $1 million, right? But any action you do on day 3, none of that's going to get you the $1 million as a direct reward, right? But you could build a value function, iteratively, algorithmically, or however, right? That is something that's designed to guide you to that reward. Oh, I want to make an alliance. I want to not get voted out. That's an important part of winning the $1 million, right? Okay, but it's a way of navigating you to a distant reward. Okay, so that's how we motivate the idea of a value function. Okay, those are a lot of the key components. All right, now this particular implementation, this is called dynamic programming. Okay, The idea is that you have a way of either iterating the value. You can either or you could iterate the policy, okay? The way that we just built, we basically built a policy that says, hey, just go to the state that has the highest value nearby, right? But keep iterating on the value until that policy makes sense. You could also just keep updating a policy of what you do in a given state, run the policy, and then see what the value is of that policy. So that is called, so we call these value iteration versus policy iteration. Okay. Now, you will notice, so this idea of dynamic programming and sort of dynamically updating all these little elements of your value function and things like that. It's a very counterintuitive term. What does it have to do with, you know, programming especially, or being dynamic? The story is that Richard Bellman in the, I think the 60s, who invented the term and invented the technique. He, like all of us, like all of us researchers, we were looking for funding for our research. And we all have different ways of getting funding for our research from different government agencies, sometimes different companies. He got his from the Department of Defense, and like a lot of people do in the field. And typically, there's what's called a program officer at a government agency who's in charge of deciding who gets money. Like, I like that idea, I don't like that idea. So a lot of your job as a researcher is selling your idea to program officers and the people that help review the grant proposal to program officers. So part of that is salesmanship. This is this cool idea I've got, like, and it's like, and this is what it can do, this is what it's about. But sometimes these program officers have particular biases, and like this particular program officer hated math. Didn't like math, or at least didn't like mathematical research. Thought mathematical research was not a good use of the dollars he was giving out. So he's like, okay, I can't use anything with the word math. So we'll call it programming. That's way cooler. Isn't that neat? And then he said, wait, I'll call it dynamic programming. Do you know why? Even though it's because it's impossible to use the word dynamic as an insult. Was Richard Bellman's reasoning. So now it's stuck with dynamic programming. That's what it's called. I think it's chapter 4 of the Sutton and Bartow text. So, you know, it's all about salesmanship, folks. And sure enough, that's what we've got. That's dynamic programming. The idea of iteratively updating the value, or iteratively updating the policy. Okay. All right. So we have these core concepts. So let's flesh them out a little bit. Okay. The idea of state. Okay. A state is a set of variables which describe an agent's current relationship to an environment. And this is highly similar to control system states, okay? So, in this grid world example, okay, I was in a certain block. That was my state. That told me where I was in that environment, right? Okay. If your state, so that could be a row and a column that I am in that environment, right? That describes everything I need to know about where I am. Okay? If I have every piece of information that I need to describe the game in that state, okay, then there's a name for that. It's called a Markov system, okay? It's a Markov state. So basically, like imagine we're playing chess, right? Playing chess. Chess is a classic example where if you look at the board, does anyone play chess? Your chess is popular. Ever since Queen's Gambit, I think it got popular. Okay. So all you need to know is the board and whose turn it is, right? That's all you need to know about chess. That's it. Okay? We would say that representation of the game is Markov. Okay? I'll just write it out and then I'll define it like Markov. Okay? There's no hidden information. Now, if for some reason, I think that Elon Musk said chess is too boring for him because there's no fog of war in chess. And I'm like, okay, whatever, dude. Whatever. Play StarCraft or something then if you want that. But fog of war meaning you like, oh man, it's like, anyway, Elon. Whatever, my guy. Okay. So but like imagine you put a veil in front of all your opponent's pieces, right? You don't see everything. There's hidden states. That's non-Markov. Okay? So a representation of states is Markov if it contains all necessary information. Okay? For the environment. In chess, you know where all the pieces are, you know if it's your turn or not, that's all you need to know. Okay? You could get more complicated. You could say, it's like, well, what if you're playing against an opponent who's tired? You know? Maybe that's a state that's important. If they're going to make worse decisions. Like, well, if you're considering a game where that matters, then maybe you do need that information in your state in order for the game to be Markov. Okay? And the beautiful thing is that if your system is Markov, then if you know your state, you could then know everything you need to know in order to create a good action, right? Assuming that you actually optimize your policy well enough. Okay? Okay. So that's a system state. And so far, we've been talking about it in terms of a grid. Okay? So so an example controlling a pendulum. I'm sorry, my optimal controls class. I'm going to see it again. Okay? Imagine you have a pendulum that you want to swing under gravity. You have a torque that you can apply, tau, that's your action. Okay? And you want to swing it up to the top. Okay? You want to find a policy that swings the pendulum to the top. And for that, we need to define our states, our action, and define our action, A, and the reward, R of S and A. Okay, that's just to set up set up our reinforcement learning problem, right? Okay. We want to find a policy pi. You know, pi takes in a state and it gives us an action. Okay. But to even set up this problem, we want to come up with a Markov state. So what are all the information that we would need about this pendulum to make a decision? Okay. Well, intuitively, you'd want to know the angle of the pendulum. Let's draw that. Theta. Okay. Is that all you need to know? We're going to apply a torque to get it to the top? No, I'll call on you, Christian. I'll give it to you. What are you thinking? The length? Okay, we'll give you the length of the pendulum. That's a mistake on my part. I'll put the length of the pendulum on there. Okay. Good on you. Good on you, Christian. Great name, by the way. All right. So, anything else? So you need to know in your system state, because, well, the thing is, the L never changes. Okay, it's part of the environment. Okay. When I talk about state, these are things that change over time. Okay, or can change over time. All right. Anything else? Omega, your rate of change. Right? Because let's say you're at the top. You're like, oh, fantastic. I don't have to do anything. Oh, wait, you're moving at Mach 3. Never mind. The speed's important. Okay? And for those who take control systems, we have we call that a state space representation, where you actually know the number of variables you need in a dynamical system to represent, like as a moving system, how many states do you need? Okay? And the life hack is to say, well, what's the order of the differential equation that defines it? That's the quick hack for it. For the greater hack, just take my class or take Controls 1, which I'm offering. If you want to learn the dynamics of a pendulum 50 times, just take my advanced control system, my advanced dynamics controls system, my advanced dynamics class that I'm also offering. Just take everything. Who cares? Okay. Why not at this point? All right. So we got to define our states. Our states, we'll define them as being our angle and our time derivative of our angle. So we'll just say d theta dt. Or as Jack said, omega, as we often know, right? Okay. Doing good? Fantastic. Those are our states. Okay. What's our action? Our action is the thing that we get to decide that comes out of that policy. What is that for this context? Tau! Yeah, sorry, I heard a very high-pitched tau. It's higher pitched than I expected. Tau, right? That's the torque that we're applying to that pendulum. It's like a motor applying a torque. Like a cat. Let's see. All right. Torque on the pendulum. That's the action. Okay? Gesundheit. Now, if you're a clever little controls dweeb like I am, you can be like, oh, I'm going to do a PD controller on that. That's my policy. That could be. That could be your policy, all right? Good on you, naughty kid. All right, so we got that. So that's your states, that's your action, right? But from a reinforcement learning standpoint, we want to learn what the best policy is. We could represent all the different states that we could be in and try to find out what action we should apply. So here's the simplest way would be to have a gridded representation, right? Where we could represent our state as a grid of both of our two different states we can apply. We could have on this axis, we could have theta. In this axis, we could have omega. And just grid it. Those are all the states we could be in. Doesn't need to be a grid, but it's just easy to envision as a grid, right? I could be pendulum way at the bottom at a certain speed, a pendulum way at the bottom with no speed, with a high speed or something, right? Or this could be, -1, this could be 1, this could be 0, this is minus pi, this is pi, that's 0. You have a bunch of different grid points, right? And we know, and we could say that we want our reward to be that if we get to the top, which is angle, this is pi. Pi is at the top. Okay, friends, we're going to change this. We're going to make this 0. So 0 is right there in the middle. And right there, that's pi. Wait, gosh, I just did it again. I'm sorry. That's pi. That's 2 pi. That's 0. We want to go from the bottom, which is 0, up to pi. We remember radians, right? Oh my gosh, there's 2 kinds of pi's. Pi is exactly 3, okay? 3.14. This is 6.28. Okay, sorry. This is why you don't mess with pi. But anyway, machine learning scientists, fired the first shot. What can I say? All right, right? Well, where do we want to be? We want to be right there. We want to be up at pi with 0 speed, right? Okay. And you could have a set of actions. You could have a set of actions that look like this. You could have actions that are also a grid, right? You could say the action, this could be do 0 Newton meters of torque. This could be minus 10 Newton meters of torque. This could be 10 Newton meters of torque, right? That's the number of actions that you could have as they're all enumerated. We call it the action space. And this space of possible states we could be in, what do we think we call that, friends? State space. Right? We have an action space and a state space. Oh, great. Cool, I've represented my state space, my action space. Now I'm going to say that the reward is 1 here, 0 everywhere else. Okay? That's our setup. We have defined the action space. We have defined the state space. We've defined the reward. Okay? That's a big part of the setup. Now, if we want to use dynamic programming, we could decide to iterate policy or value. Okay? So we could either try to create a policy, which we say, hey, if we're in this square, we do this action, right? We could change up that policy somehow and see if it makes the value better. Or we could take a policy that is just looking at the value and then just keep updating the value until it gets better. Okay? And you can create a bunch of values across this whole grid, and you say, oh, if I am in this state, which action transitions me to another state with a high value? Now, this is where it gets a little complicated, my friends, because unlike my grid example here, right, where if I can only move in a grid-like way, right? With the pendulum, the way I've set up this state space, that's not necessarily the case. Okay? If I'm in this state, and then for just like a short period of time, I apply 10 Newton meters of torque, right? When I go and measure again, I might be all the way over here, or all the way up here, right? Okay? So basically, we have to consider the way that we transition. Okay? So we must consider how each action transitions to the next state. So we have a policy, okay? We have some action. So let's say we're going to transition from some state I by means of some action, it goes to some other state, I plus 1. Okay. So so how you represent a state transition is called a Markov decision process, or MDP. I'll give you an example. So anyway, like I'm kind of shuttling away from the pendulum example. I'm showing you the way that you sort of represent the state here. Okay. Now we're going to get to how we actually, a little meat of how we're actually going to compute this with whatever little time we have left. Okay. So this is my favorite example. I remember I was a wee baby grad student. I was trying to come up with an example that made sense to me. Okay. I'm going to draw my friend frog. Okay, he's happy. He'll smirk. Okay. Frog. This frog you can tell because he's green. All right. And he's on a lily pad. You can tell, also green. And it's on water because of drag scattering. It's blue or whatever, okay? This is his state. He's on state 0. Okay? And this frog looks too sad. Too early to be sad. There you go. Thank you. Happy frog. Okay? He could be on another state. Lily pad 1. Lily pad -1. And draw some more lily pads, okay? They're all equivalent lily pads, but I'm running out of space, okay? But at the end, past here, it's an alligator. It's green. And over here, another alligator. Green. Okay? We're doing science here. No laughing. Okay? So you have state -2, state 2, state 3, state -3. Okay? Now let's say that this frog has a policy. At 50% of the time, hops to the left. 50% of the time, hops to the right. Okay? I'm going to construct a Markov decision process that describes how he or she transitions from lily pad to lily pad. Okay? All right? So here I'm going to have state I, and then state I plus 1. So my first state to my next state. All right? And let's see, I'm going to say it's a -3, -2, -1, 0, 1, 2, 3. Move this all down. I'm going to make basically a grid of 7 by 7 grid here. I could have made this simpler, but why? -3, 2, 1, 0, -3, -2, -1, 0, 1, 2, 3. Okay. I think you got that here. 1, 2, 3, 4, 5, 6. Perfect. 1, 2, 3, 4, 5, 6. Perfect. Okay, thank you very much. Okay. So this frog has a 50% chance of going in either direction each jump. Okay? So if he or she starts out at state 0, okay, what are the odds it's going to end up after one jump in -3? 0. -2. 0. -1. 50%. I'll do 0.5. Okay. 0. 0. 50%. Okay. Let's say the frog is on, and it's always the policy, it's going to try to jump left or right, much to its future demise. Okay? And I hope it goes without saying, unfortunately, once it ends up in the gator, it's going nowhere. Okay? All right? All right? So if it starts out in -1, it's going to be 50%, it's going to end up in -2, 50% in 0, right? You can follow this, you can see where this pattern is going, right? 0 everywhere else, right? If it ends up in -3 in the gator, 100%, it stays in the gator. Sorry to say. Same with our other gator compatriot off to the right. Okay? That's your Markov decision process, or MDP. Okay? Because our system is Markov, okay, we can describe our system completely in terms of system state. And for a given policy or transition method, okay, if you start in a certain state, what are the probabilities you're going to start off in end up in other states, right? Now, right now, our state is one-dimensional. You'll notice that I only have states in one direction, right? You know, it's not a two-dimensional field of lily pads, right? If I were to make this, I'd have to take every single one of the states from all the different combinations and extend this out, blah, 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 blah. It becomes big very quickly, right? People understand that? So imagine if I had a field of lily pads, instead of having, I don't know, how many gators are we going to want around the edge of this thing? There's a lot of gators. Let's assume that if it ever jumps in the water, the gator's going to get it. I don't know, okay? Right? Say it's 7 by 7. All of a sudden, you're going to have 49 by 49. Doing extreme eye padding right now. I hope you appreciate, right? Right? So 49 by 49. So we had a second state. It gets bigger. You could make an MDP like this, and you can use this to train a policy. Okay, value iteration and others, right? And in fact, for, here we have, for the pendulum, for a pendulum, a two-dimensional state, right? We could do that. Hopefully we'll actually get to code this up from scratch in class with either value iteration or policy iteration. But let's say that our policy, or our pendulum, was not one pendulum, but it was another pendulum on the end. We actually have to add 2 more states. Now it's like a 4-dimensional grid we're dealing with. Add another pendulum. 6-dimensional grid. I cease the ability to draw it anymore. Okay? And tell you, you're dealing with dynamical systems. This I need a demonstrator marker. Okay? Well, watch out, I'm going to try something. 12-dimensional grid for that thing. Position and speed in this direction, 2. Position and speed in this direction, 2. Position and speed this direction, 2. 6. Math is fun. Yaw, extra 2. Pitch, extra 2. Roll, extra 2. 12-dimensional state space. It's tricky quickly. So these dynamic programming methods were great for limited numbers of states for many, many years. But as those states blow up, the amount of grid points you would have to put on a grid would blow up, and that's not good. That's what we had called in the past the curse of dimensionality. Sounds like a sci-fi novel. Recursive dimensionality, right? It's only good for so many states. Let me take up these before I start tripping over them. Excuse me. Have my prop comedy going. All right. So what was the solution? But thankfully, there's a solution for representing high-dimensional spaces that we've gotten really good at learning how to train. Artificial neural networks. Okay? So once we really figured out how to train with big data artificial neural networks, we had a really good solution to recursive dimensionality. Okay? So instead of representing your state space like a grid, I might represent it as a neural network, or specifically, the policy. Here's my policy. Where in goes a state, neural networks. Okay? Where in goes your state, here's state 1, here's state 2, up through state n, into neural networks. Here's just a simple multi-layer perceptron neural network. Okay. And then out would come your action. And it could be multiple actions. You know, that's just action 1, right? Okay. So neural networks offer a way to represent a policy in spite of a lot of states or many actions. But the thing you need a lot of to train a neural network, data. Okay? So what we found is that it's really important to have a way to try lots of possible different policies in order to train this neural network to have a higher reward. Okay? When it comes to physical systems, it's not often the easiest. It is possible. It is definitely possible to use a physical system. Imagine you're doing a power plant, right? If you wanted to train your power plant to have a reinforcement learning policy that runs it, you know, you don't want that power plant to explode lots of times to learn a good policy, right? But what do people turn to instead? Computer simulations. In a computer simulation, when something blows up, the only thing it hurts is my feelings. Okay? All right? So this is really motivated in robotics and many other fields, creating good computer simulations to try out lots of policies. Okay? Right in the lab right over there, where my lab works and other robotics labs work, we will run computer simulations on GPUs. Remember GPUs? What's a GPU? Anyone remember from lecture number bleh? Graphics processing, graphics processing unit, right? Okay. They're very good at parallelizing and doing matrix math, okay, and doing lots of parallel operations, right? We found out good ways to run not just one computer simulation at a time, but run many in parallel and try out how they work, okay? And that gives us a lot of data with which to train a neural network. Okay, and we train the neural network in a computer simulation, then we put it on the actual physical device and hope it works. If you have a good simulation, there's a good chance, right? But it's not magic. Okay, there's still there's still lots of catches. Who chooses the reward function? We do. Some reward functions are more helpful than others. So we have a quadrupedal robot, robot dog. You grab a robot dog? You pull out the robot dog's in the lab right now, right? Would you mind grabbing it real fast? Thank you so much. Yeah. It won't run. I'll just show it to you. Okay. It will run, but don't let the professor try to run it. That's a bad idea. Okay. All right. So this robot dog, so my student Jacob was really doing a lot of the reinforcement learning work, particularly with deep learning, with deep neural networks. If there's a deep neural network involved, it's called deep reinforcement learning. Write that out here real quick. Reinforcement learning. or DRL. Okay? So we got this robot dog. Okay? And we want what kind of reward do we want to tell it in order to get it to move around the world? Okay? And Sam, you were working with the deep reinforcement learning of the robot dog at one point, right? And you would, so what we would come up with a reward function, and it would be like, we would give it a command. We want it to go forward, and the more it would go forward, the more the reward, okay? But that's also often not enough, because what it might try when it's training is it might just flop its belly on the ground and go. So in order to guide it in order to be able to move better, we'll say, hey, actually, keep your body off the ground, please. We will reward you keeping your body off the ground, maybe at a certain height, okay? Is that necessary for locomotion? Not necessarily. You could totally get on the ground and do that. It's probably just a bad idea, right? But we start to shape the reward and what we think is a good idea. And what maybe using too much of the motors is a bad idea. So maybe we'll start adding different reward components. So we have a reward that might equal, going forward. And keep your body off the ground. Off the ground. And what did I just talk about? I just did a thing. Motors, less motor. Less motor effort. And the way we would say it is, hey, it's the squared value of the torque, so the less motor. Feet slipping, you'll notice that when we run the robot, it's like its feet are slipping. It's like its feet are slipping, and it sounds bad. Like, don't slip the feet. Plus, it's actually working. Oh, thanks, Jacob. Anyway, it's actually running. It's okay if we bring it down here. Yeah, there is a ramp over there. Okay, what a surprise! Surprise, special guest here. I didn't. This is unplanned. We have a special guest here. Thank you, Jacob. I was just going to hold it up, but this is way more interesting. All right. All right. Let's come right over in here in front of everybody. Like I planned this, but I absolutely didn't. All right, here we go. This is the Unitree Go-To. This is from the Unitree family of robots, okay? This is Jacob here. Jacob, why don't you step? Are you comfortable being in front of the camera, in front of the world? Sure, yes, he is. Thank you. All right, so this is Jacob Hackett, one of our PhD students. He's in charge of he's in charge of our deep reinforcement learning methods. So would you mind talking a little bit? I'm going to hold this in front of you like you're a Gen Z YouTuber, okay?
Yeah.
All right. All right. So yeah, tell us a little bit about the reward function that you have for this guy right here.
Complex.
It's complex.
It is complex, yeah.
Okay. How so? What's in it? Give us some ideas of what's in it.
So you have these positive terms, which is typically aligned with the task that we're trying to do. So if I were to make a reward function that resulted in a controller that can move left, right, forward, backwards, these are velocities that I'm tracking. Same as some sort of angular rate. That's also some sort of velocity I'm tracking. So that would be our positive rewards. But then there's everything else that we don't want it to do. So we have to do a lot of penalties. And so we penalize essentially things like orientation. I don't want you to move your body in weird ways. We penalize it so that we can find a certain gait. So we would do things like you need to have your foot up in the air for a certain amount of time. So things like that.
Yeah. I was talking about, but you're also telling it to hit a certain height of the body, right? Like
not necessarily.
Really?
Yeah.
So how do you prevent it from flopping around on the ground? Does it figure that out on its own? Or
it does. Yep. So
okay, wow.
In this case, that's emergent from here, so it can figure out what it needs to be.
Yeah.
But that's also from a consequence of other things in there that might be encoded.
So can you give our esteemed audience here of people who pay tuition to be here an idea of how of the number of computer simulations it takes to run and generate a policy like this? Just a rough estimate.
Hundreds of millions of experiences.
So is that including just time step to time step?
Time step to time step.
Okay, so when you say experience, you mean from time step to time step. That's how many milliseconds between time steps here?
0.02. So it's a 50 hertz control rate. So
okay.
Yeah, that much.
So every 50th of a second, it's measuring. Is my foot off the ground? Is that a good thing? Am I moving forward at the speed that you desire? Is that a good thing? All inside a computer simulation, hundreds of millions of times.
Yep.
That's all.
Yep.
That's all it's involved. Okay. But why is that possible? How does it, is there one CPU running 100 million time steps? I say forebodingly.
No, there's a GPU that can parallelize all this at once, so it's tractable. So so I'm simulating this robot 8,192 times, and we're forwarding that through time. So we collect a lot of examples pretty quick.
Yeah, and so, those 8,000 times, that's one epoch, that's one generation, and then you update the neural network for the next policy, and then so on and so forth.
Yeah.
Let's give a round of applause to Jacob. He did that in no time at all. All right, I think it's a good place to end it. Yes, I think we got one last question before we go. Yes. Yeah.
The stock unit.
Yeah. Yes.
So in simulation.
Yeah. Yeah. Say other questions. Yeah. And Jacob was pointing out, these are the stock controllers. These are nice. These are the stock controllers. So this one is actually probably not deep RL, right? So this controller is probably actually using MPC for if people are taking my optimal controls class. So I should say, but Jacob has just submitted a paper on some really cool deep reinforcement learning control. Just to be clear for people watching, this is a more traditional control policy, but deep RL does a really great job. All right, cool. Thank you everybody so much. Good luck on the homework.